Hello, in this last video in this unit, I'm going to talk about the relationship between conditionals and disjunctions. So, every conditional can be translated into a disjunction and vice versa. There's what you can say with conditionals, you can say the same thing using disjunctions instead. And what you can say with disjunctions, you can say with conditionals instead. So in particular, P or Q, that's equivalent to if not P, then Q. Either both are true or both are false. They never disagree. It's never the case that one of those is true and the other is false. So there's a theorem that tells us this. This theorem says P or Q, if and only if not P, then Q. This is valid. It's always true. With our current rules, so it's biconditional, so we can think of it as being made up of two conditionals, from the left to the right and the right to the left. So as it turns out, right now, with the rules we have, we cannot derive the right to left version, the right to left conditional in this biconditional. That is, we cannot derive if it's the case that if not P then Q, then it's the case that P or Q. Right now we cannot derive that conditional, but we'll see how to derive it in the next unit when we introduce a new method of boxing and canceling and making assumptions called indirect derivation. And the other direction, the left to right direction, if P or Q, then if not P, then Q, that is derivable. And I'm going to show you how to derive it right now. So here we have our conclusion. Since this conditional is always true, we should be able to derive it without using any premises. So our first line is show if P or Q, then if not P, then Q. Well, second step on our strategy is always to make an assumption if we can, and we can make assumptions if we're trying to show a conditional. We can assume that the antecedent is true for conditional derivation, and that's what we'll do there. Now, there are no premises to bring in. The next step then would be to look for inference rule applications. We could do all the introduction rules we wanted, but this would be, this is clearly pointless and will get us nowhere. The introduction rules are not going to help. Will the elimination rules help? Well, there are no elimination rules that we can apply. We would need negation P or negation Q for MTP with line 2, but all we have is line 2. So the derivation is stuck, and what do we do when our derivation is stuck? We do a subderivation. We want to do a subderivation that will help us complete the main derivation. So that will help us box and cancel line 1. What will help us box and cancel line 1? The consequent of line 1, because then we can apply CD. So we're going to show the consequent of line 1. We're going to show if not P, then Q. Well, whenever we enter a show line, we want to make an assumption if we can, and we can because we're trying to show a conditional, so we can assume that not P is true for a conditional derivation. So here we have not P. Now we want to ask, now that we have this new line, can we do anything with it? And the answer is we sure can. We can apply MTP to lines 2 and 4, and we get Q. What can we do with Q? We can box and cancel line 3 because Q is the antecedent of line 3. So we can say 5 CD, and that completes the subderivation. We now want to use this line 3 that we just canceled. And what do we want to do with it? We want to, well, if we look, we remember we did this for show cons, which means that 3 is the consequent of line 1, which means that we can box and cancel using CD applied to 3. And that is our derivation. So there you go, an example of conditional derivation showing that if P or Q is true, then also if not P, then Q is true. So that's the last derivation example. If you have any questions about any of the derivations or symbolizations, please let me know. Good luck with your homework.